बिस्मिल्लाहिर्रहमानिर्रहीम। अज़ीज़ तलबा व तलबात, आज हम C13 के बारे में C13 NMR या C13 MR कार्बन 13 न्यूक्लियर मैग्नेटिक रेजोनेंस और C13 Nmr resonance, or it is also called as CMR, carbon nuclear magnetic resonance. In the CMR, here it is used for the determination of the number of the carbon atoms in the compound, particularly C13 carbon atoms which are present in the molecule. We have studied PMR, proton nuclear magnetic resonance, PMR, or HMR, proton nuclear magnetic resonance, is used for determination of the number of equivalent set or number of non-equivalent sets in a molecule, and the number of the hydrogen or proton in each equivalent set. This can be determined by the use of the PMR or proton nuclear magnetic resonance. So in this way the structure of the molecule can be determined. Here in the CMR, CMR is used for the determination of the number of the carbon atoms, and sometimes the number of hydrogens which are present on a carbon 13, that can also be determined by the use of the CMR. So carbon-carbon chain which is present in the organic molecule, or the carbon-carbon linked ring structure which are present in the molecule, or the methyl group or methylene group or methane group, carbon can be determined by the use of C13 NMR or C13 MR. C13 NMR or MR is not as widely used and is not as widely used as the PMR or proton nuclear magnetic resonance, due to the fact that there are present very small number of the C13 carbon atoms, which is 1.1% abundance is relative abundance of the C13 is 1.1% as compared to the C12 carbon which is present in greater abundance. C12 or 6C12 is NMR inactive because it has no net nuclear spin, so no net magnetic moment or magnetic properties, due to which 6C12 cannot be studied in the NMR spectroscopy. So only 6C13 which has net nuclear spin and which has magnetic moment and this C13 can be used in the nuclear magnetic resonance. Here you can see that in the C13 Nmr, since organic compounds contain carbon atom essentially, so CNMR or CMR spectroscopy would be very useful. But unfortunately, what happens, since the relative abundance of the C13 is only 1.1%, so what happens, this less abundance of the 1.1% has the result, and what is the result, that the carbon NMR spectra, the relative abundance of the C13 suggests that the C13 NMR spectra should have the signals which is 1.1% as intense, or has the height only 1.1% as compared to that of the proton NMR. Or in other words, the height of the peak or area under the peak is very small as compared to that of the signal of the PMR. Now, in other words, carbon NMR signal is about 0.015 times as intense as that of the proton signal. So very small peak, in very simple words, very small peaks of the C13 signals are obtained in the C13 NMR spectroscopy as compared to the signals of the proton in the PMR or proton nuclear magnetic resonance. Now here it is calculated more accurately that the intensity of the carbon resonance or carbon peak is, this is exact, 0.00175 times as intense as that of the peak of the proton. So in very simple word, it is very small peak. Very small peaks in the NMR spectrum are obtained for the C13 as compared to the signal of the protons in the proton nuclear magnetic resonance. Now, how it is done? Here there is also present what this is one problem is which one problem due to which the C13 NMR is less widely used as compared to the proton NMR is the less abundance of the C13 NMR, 1.1% of as compared to that of the 6C12. Since 6C12 is NMR inactive, only C13 is NMR active, and C13 has only 1.1% abundance, so it will give a very small peak as compared to that of the proton peaks or signal in the NMR spectrum. So this is one reason why C13 is not as widely used as proton nuclear magnetic resonance spectroscopy is used. Then how this problem is overcome? There is also present electronic noise is also present. Noise here means due to the one type of the interaction, very small peaks are obtained. Those are also called as noise. Very small peak as compared to the relatively large peaks of C13. Those are also called as noise. Those noise can be produced, those very small peak as एक तो comparison है किसका, signal of the proton peak with the signal of the C13 peak. फिर C13 peak के अंदर उसकी relatively very small peaks जो हैं वो as compared to C13 peaks, उनको हम noise कहते हैं. That is also due to different reason. एक तो रीज़न उसमें इलेक्ट्रॉनिक नॉइज़ भी हो सकती है, which is unwanted disturbance in electrical signals, या due to some type of the spin splitting, electronic noise is present. So how this problem is overcome? इस प्रॉब्लम पे हम कैसे काबू पाते हैं? किस प्रॉब्लम पे कि इसकी पीक जो है वो बहुत छोटी होती हैं किसके मुकाबले में, एज़ कंपेयर टू दी प्रोटॉन NMR peaks. Now you can see that roundabout we are taking many spectras. We are taking many spectras of the C13 containing compound. Roundabout how many? 6,000 spectras. 6,000 spectras of the carbon 13 Nmr are taken, and they are added together to get the same intensity as that of the signal of the proton in the PMR spectroscopy. So 6,000 CMR spectra, carbon 13 NMR spectra should be and must be added together in order to get the same intensity or same height of the signal as it is present in the proton NMR. Now the CMR, so these were the problems. Number one, very small abundance of the C13. which will lead to the formation of very small peaks in the CMR. And how much small peak? That if 6,000 CMR peaks or signal of the C13 are added together, then it will be equal to one signal of the PMR or proton nuclear magnetic resonance. So these were the problem which were present in the C13 NMR. Now the principles of basic principles of the C13 NMR or CMR and proton NMR are essentially the same. What are those basic principles? First is the coupling or splitting between carbon is not observed because C13 is in very small abundance, so rarely two C13 are present on adjacent position. And if it is enriched, then that will be if enriched carbon is present, enriched will be that in which C13 abundance or the concentration of the carbon, or the number of the carbons are increased, C13 carbons are increased, that will be enriched carbon containing compounds. Enriched C13 enriched compound can be prepared easily, and if C13s are present on the adjacent carbon atoms on adjacent positions, C13 carbons are present on adjacent position, then it will produce similar type of the splitting as it was present in the proton NMR spectroscopy. So this is very unique that no CC coupling is usually observed, since C13s are very rare. So CC coupling is very rare. But if you are increasing the C13 concentration, C13 number of the carbon atoms in a molecule, or which is called as enriched C13, then coupling or splitting will be same as it is present in the proton NMR. Second important aspect of the CMR is the range of the chemical shifts. Range of the chemical shift. Chemical shift, we have seen that the relative separation of a signal of a proton as compared to the signal of the protons of the TMS is called as chemical shift. So chemical shift scale, you can say, chemical shift scale in the PMR or proton NMR is usually delta 0 to 10, but here scale is very large. How much large? It is usually 220 0 to 200 pm, a range of 200 pm or 228 pm, 0 to 200 pm is present here. 0 to 200 or 228 ppm scale is present. for the measurement of the chemical shift, unlike that of the protons, where chemical shift scale is usually between 0 to 10 ppm. So in this way, this is a unique characteristic of the C13 Nmr spectroscopy or C13 Nmr spectrum or CMR. And another very important point is that chemical shift in the CMR are more sensitive to small changes in chemical environment, which will lead to but chemical shift in the CMR are more sensitive to small changes in the chemical environment as compared to the PMR. And this point can be explained by taking the example of this compound. This is 3-methyl pentane. 1, 2, 3, 4, 5, 3-methyl pentane. And in 3-methyl pentane, here you can see CH3, CH2, CH, CH2, CH3 and CH3 are present. Now highly branched carbon typically have greater chemical shift, than that of the unbranched one. This one. Highly branched carbon typically have greater chemical shifts than unbranched one. So here you can see this is 11.3 and here it is 18.6. Which is more branched? This carbon. Here it is CH3, it has only one branch. This CH2 has two branches. This CH has three branches. So this carbon has 36.2 ppm. This carbon has two carbon, it has 29.3. It is less branched, it has 11.3. So as the branches are increased, the chemical shift value is also increased. So this is another unique characteristic of the CMR spectrum. And another important and third unique aspect of CMR is that splitting of C13 resonance by proton is very large. Typically coupling constants are in the range of 120 to 200 Hz. Chemical shift value is also more than that. Chemical shift scale has more value as compared to proton PMR. In PMR 0 to 10 ppm is present delta, and in the C13 Nmr it is 0 to 200 or 228 ppm. Here another important characteristic is present. The coupling constant is the separation or the distance between the two split peaks, and it has been explained earlier that the value is between 0 to 18 Hz. Distance between two split peak is between 0 to 18 Hz in the PMR, while here the distance between these two split peak is 120 to 200 Hz. It is very large as compared to that of the PMR. Now what will be the effect of this greater separation of the two split peaks or greater value of the coupling constant 120 to 200, that many signal or peak will overlap over one another. So many signals cannot be observed in this way due to overlapping. Now in most of the CMR splitting is eliminated by a technique which is called proton spin decoupling, in which the protons coupling has been eliminated or removed. This type of the technique is called as proton decoupled CMR spectra. Proton decoupled proton decoupled C13 Nmr spectra. Usually C13 and proton can interact and will lead to the splitting of the peaks, and splitting of the peaks, the distance between the peaks will be 120 to 200 Hz. 120 to 200 Hz, and which will lead to the overlapping of many signals. And secondly, when the splitting of the signal is observed, then the intensity and height of the peak is further decreased. So to overcome this problem, proton decoupled C13 spectra is used. Proton decoupled spectra is used. Now these points are illustrated by this example. Here, 1 chlorohexane, and we are supposing that all the carbons are C13, and if it is proton decoupled, then one peak of TMS will be obtained. Another peak is for A type of the protons are present here. It is shielded. Then B is less shielded as compared to A. So here you can see this is a peak or signal for B type of the protons. This is a peak for C type of the protons. This is a peak for D type of the protons. This is a peak for E type of the protons, and this is a peak for F type of the protons. As the electronegative atom is nearer, so it will be more deshielded and more d-shielded will be present downfield, and it is present downfield and it has greater value of the delta. So F type of the proton has maximum value of the chemical shift as compared to A type of the proton, B type of the proton, C type, D type and E type of the protons. So 1, 2, 3, 4, 1, 2, 3, 4, 5 and 6 signals, 6 lines are present in the spectrum. Now you can see this is this similar point as it was present in the PMR, that more d-shielded protons are present downfield and have greater value of delta. Same is the case here. Now here you can see another important point. To differentiate between the compounds, which one? Here 1 chloro and 3 chloropentane, 1 chloropentane and 3 chloropentane, two compounds are present, and proton decoupled CMR spectrum of 1 chloropentane should consist of 5 lines. 1 chloropentane. 1 chloropentane has 1, 2, 3, 4 and 5 carbons. So its NMR spectrum should consist of the 5 lines. But the 3 chloropentane, you can draw the structure of these two to clarify yourself more. 1 chloropentane and 3 chloropentane. 1 chloropentane will give 5 signal or 5 peak in the NMR C13 Nmr spectrum, and 3 chloropentane will give how much? Only 3 lines. The 2 CH3 carbons are and 2 CH2 carbons are similar in compound which is called as 3 chloropentane. So 1 chloropentane will give 5 lines and 3 chloropentane will give only 3 lines. So these two can be differentiated on the basis of the CMR. Many decoupling techniques in which the proton nuclei cannot interact with the C13 nuclei, so splitting of the peaks will be decreased. It is possible to determine which carbon signal in CMR spectrum comes from methyl, methylene, methine or quaternary carbon. One such technique is called as DEPT. DEPT, this one. DEPT, distortionless enhancement. Distortionless enhancement with polarization transfer. DEPT yields DEPT yields a separate spectra for methyl, methylene, methane carbons. Now each line in the spectrum corresponds. Each line in the spectrum corresponds to the line in the complete CMR spectrum, and the lines which will not appear in the DEPT spectra are assumed to arise from the carbon that have no hydrogen atoms. Here you can see how it can be C13 Nmr can be used to identify and to distinguish between the different carbon atoms. Here we have two compounds in which this is methyl group, 1 2 3 4 1,4 dimethyl benzene. And how many signal in the CMR are formed? C13 Nmr, and we assume that all carbons are of C13. Here you can see this carbon and this carbons have similar shielding and de-shielding effect. So one set is formed of these two. This is represented by A. This carbon and this carbon are these in similar environment, so it is B. These four carbons are present in the same environment, so it is C. 3 signals will be given for this compound. And how many for this? This is A type of the proton, B type of the proton, A type of the carbon, B type of the carbon, C type of the carbon, and D type of the carbons. How many? 4 type, 1, 2, 3, and 4 type of the carbons are present, will give the 4 signals in the NMR spectrum. Similarly, other examples can be seen here. This is another example how spectra C13 spectra of these two compounds differ from one another. Here this is A, B, A. These two carbons are similar, AA. These two carbons are similar, BB. This carbon is similar to none, so it is C type and D type. 4 type of the signals are obtained in these compounds. And how many? This BB are the same, these 4 carbons are same. This A and A are same. So 1 and 2 type of the signals are obtained in the C13 NMR spectrum. So these are important characteristics, important points which are associated with C13 Nmr C13 Nmr spectroscopy. Some more points are present on the pages which I have already sent. So by combining these two things, this video lecture and those pages, I think you will be able to understand completely what is C13 Nmr spectroscopy and how it is different from the PMR or proton nuclear magnetic resonance spectroscopy. Okay, then खुदा हाफिज़. नेक्स्ट टाइम इंशाल्लाह हम कोई और टॉपिक का करेंगे.